says, in many applications of integration, you are given enough information to determine a particular solution. To do this, you need only know the value of y equals f of x for one value of x. This instance is called an initial condition. So if you know 1 point, on the graph, then you know what C needs to be, or you could figure it out. It says only one curve passes through the point 2, 4. That was the blue curve that we highlighted on the previous page. To find this curve, you can find the general solution, which we did, and then you can use that initial condition. We wanted the initial condition that it goes through the point 2, 4. So look at the math here. What you have is your general solution, f of x equals x cubed minus x plus c. Well, we know when we plug in a 2, we need to get a 4. So if we plugged in 2 cubed minus 2 plus c, we know it has to equal 4. Well, that's 2 cubed is 8 minus 2 plus c equals 4. So that's 6 plus c equals 4. Subtract 6 from both sides and you get c equals negative 2. That is the particular solution. And so that tells me that the answer that they wanted for this problem, the one that they wanted, wasn't f of x equals x cubed minus x plus c. It was x cubed minus x minus 2. And again, that minus 2 coming from the c value that we found. So that's what they did on the previous page to find the particular solution, is they plugged in the given x value, set it equal to the y value that you wanted, and solved for c. They did this math right here, solved for c, and then rewrote their equation instead of having the plus c with that desired value, or the c value that we found. So let's look at this. It says find the general solution of f prime of x equals e to the x, and find the particular solution that satisfies the initial condition that f of 0 has to equal 3. So we're really having two answers here. We're finding the general solution and then a particular solution. So what they want us to do is find the antiderivative of, well, the function's e to the x. Well, we know that the antiderivative of e to the x is e to the x, right? The derivative of e to the x is e to the x. And I'll just write that down real quick. We know, if we check our answer, the derivative of e to the x is e to the x, so we're good there. So our general solution would be e to the x plus c. That's our general solution. But now they want a particular solution. They want the particular solution where you plug in 0, you must get 3. So again, what we have here is we have f of x, the parent function, is e to the x plus c. And what we need is f of 0 when we plug in 0, which would be e to the 0 plus c. That has to equal 3. When you plug in 0, you have to get 3. What's e to the 0? Anything raised to the 0 is 1, so we know that 1 plus c equals 3, and that tells us that c has to equal 2 by subtracting 1 from both sides. So what do? We take this c value, c equals 2, and we plug it into our answer. So our particular solution, the exact one that they wanted, they had e to the x we knew was the answer, and then we could shift it up or down. Well, to get the exact one they want, we would need to use e to the x plus 2, because that's the c value that we figured out. Notice if you plug in the value 0, you get 3, and it is the antiderivative of e to the x. So we found the general solution and the particular solution. Really, really cool there. Well, now that we know particular solutions and how this happens, what this allows us to do is go back to previous problems that we've looked at, in particular the position functions. For instance, if I dropped a ball off of a building, what would the height of that ball be? And we know that the original function was the position function. The derivative of that was the velocity function, and the derivative of that was the acceleration. We knew acceleration was constant at negative 32 feet per second caused by gravity. So could we work backwards? If we know what acceleration is, can we work backwards and find the velocity function? Well, that would just be the antiderivative of the acceleration function, right? And then can we work backwards from the velocity function and find the position function? And the answer is yes, we always can do that as long as we're given some initial conditions. So let's look at the problem here. It says a ball thrown upward has an initial velocity of 64 feet per second. So what does that tell me? An initial velocity of 64 feet per second tells me that v of 0 equals 64. The initial velocity, so the velocity at 0 seconds equals 64. And the next one says has an initial height of 80 feet. So what does that tell me? Initial height of 80 feet tells me that s of 0 has to equal 80. So that's two given bits of information, two initial conditions that I need to know. So what do I know? I know that the acceleration of t, or the antiderivative of the acceleration of t, working backwards one step up, would be the velocity of t. So what I want to do is find the antiderivative of the acceleration, which we know is 32, with respect to t. So what would that be? Well, that would be negative 32t, but then you have to have the plus c, right? So that's my velocity function. But I don't want plus c. I need to figure out what the actual velocity function is. So I need to use the fact that v of 0 equals 64. So what do I have? I'd have v of 0, which would be negative 32t, so that's where we plug in the 0, plus c has to equal 64. So if my velocity function was negative 32t plus c, and it's negative 32 times 0 plus c, so what does that tell me? That tells me that c equals 64. So what's that tell me? That tells me my velocity function was negative 32t plus 64. That's my actual velocity function for this problem. Well, if I know the velocity function, now I can find the position function. Again, the antiderivative of the velocity function has to be the position function. So let's do that. Let's find the antiderivative of our velocity function, which was negative 32t plus 64 with respect to t. And the antiderivative of negative 32t, well, that would be negative 32t squared over 2 plus 64 times t plus our constant, right? And this is our position function. But that's the general form, and we don't want the general form, we want the exact form. So how do we find the exact form? Well, we have to use our initial condition for our position. We know that the initial position was 80 feet high. So we need to use the fact that our initial position was 80 feet high. So when I plug in 0, I'd have s of 0, which by the way, if I simplified this, I should probably do that real quick. That'd be negative 16t squared plus 64t plus c. That's just the 32 over 2 is 16, right? So that's all I'm doing here. So this would be negative 16 times t. I'm plugging in the initial condition, so that's a 0 squared, plus 64 times 0 plus c, and that has to equal 80. When I plug in 0, I have to get 80. So what does that tell me? That tells me that c equals 80. So what do I know then? If I know my constant in this one, I now know my initial position function. My initial position function would have to be the negative 16t squared plus 64t plus c, but the c in this case was 80. So there it is. Let's look at it. It says find the position function given the height s as a function of time t. We just found it out, figured it out. The position function is negative 16t squared plus 64t plus 80. Okay. So I want you to remember, if you remember back when we did these problems before, we knew that s of t was always going to be, as long as it was measured in feet per second, so if feet and seconds were a unit, it was negative 16t squared plus v naught t, where v naught is your initial velocity, plus s naught. And I told you guys this numerous times, when we were doing derivatives. Well, why is that? We just proved it. This v naught, that's your initial velocity. You can see that that coefficient, that initial velocity, ends up being the coefficient on t. And you also know that s naught is your initial position. That ends up being, because of the way that it works with antiderivatives, that ends up being your constant in the position function right here. So here's our 80. That ends up being the constant in the final answer. So where does all this stem from? It stems from the fact that acceleration is always constant. So when we do the antiderivative, we would always get negative 32t plus c. So that c would always be our initial velocity. And when we integrate that, which always has to be the same, we would get that function right there, which is negative 16t squared plus whatever your initial velocity was times t plus c. And that c always has to be your initial position. So we have now proven, in a sense, just using one single case, but we have proven that the position function must be this at all points in time. Really, really cool. Let's move to part B here. What does part B say? It says, when does the ball hit the ground? Well, that's when s of t equals 0. So let's put that down. We have negative 16t squared plus 64t plus 80 equals 0. They were nice enough to use some nice numbers for us, so hopefully this turns into a nice answer. All of these are divisible by negative 16. If you didn't see that, you could have, of course, just used the quadratic formula. But I see that everything's divisible by negative 16, so this would be t squared, and then it would be, well, 64 divided by 16 would be minus 4t, and then 80 divided by negative 16 would be a minus 5, so that equals 0. I need two numbers that multiply to be negative 5 and add to be negative 4. So that'd be t minus 5 and t plus 1 equals 0. Set each of those factors equal to 0. T minus 5 equals to 0 gives me t equals 5. T plus 1 equals to 0 gives me t equals negative 1. Again, this is time, so negative doesn't make sense. So here it would be at t equals 5, and this is in terms of seconds, so this would be 5 seconds. So there it is right there. Just from knowing an initial height, an initial velocity, we are able to work backwards, knowing what acceleration is. We can find the formula that finds the exact position at any given time t, and we can find exactly how long it would take this ball to hit the ground. So if you throw it upwards with an initial velocity of 64 feet per second, at an initial height of 80 feet, as long as there isn't wind resistance, it would hit the ground at exactly 5 seconds. Really cool.